a speech technology team focused on developing voice-based solutions, including speech-to-text, voice identification, and analytics for contact centers. He earned his PhD in speech signal processing from Department of Electrical and Electronics Engineering, IIT Guwahati, in 2019, and has published 19 peer-reviewed articles. So this is a very brief about our today's resource persons. So I welcome you, Dr. Sishir, for accepting our invitation and sharing your expertise with our participants. So over to you, Sishir.
Thank you. Thank you, Officer. So first of all, I'd like to thank Officer and organizing committee for inviting me to discuss something which is very relevant nowadays and people are focusing for developing speech technology. And I actually what I saw is that Matthews are also presenting the same kind of topic. So what I modify my slides. So what I am going to do is that I'll, because sir did very interesting presentation and very insightful that, and he almost covered most of the part regarding that speech foundation model and what we can learn from that. And that's why what I am going to focus is that more about how those foundation models can learn. So we can learn those foundation models, speech foundation model. So one paradigm called self-supervised learning. So what is self-supervised learning and what those self-supervised learning representations for speech can be explored for different tasks. So that only we are going to explore, discuss in this particular presentation. So what we are going to learn is that like what are the information encoded in speech signal and what are the basic handcrafted features are there. The idea of pre-training and what is self-supervised learning, why it is more popular nowadays. Then different SSL-based pre-trained models and these models actually most of the I think speakers already discussed about those models, and then what information encoded in that SSL models and how we can use different ways to see what kind of information are encoded in that particular representations. So if we listen one speech signal, then what are the information generally it is encoded. So first, for example, whatever I am speaking now, from that first thing what you are understanding is that I am speaking in English, and then I am speaking something related to one kind of machine learning technique. Then you know like one male speaker is speaking. Then another thing what you may feel is that what is the emotion of my voice, for example, which is maybe neutral now. And those kind of emotion content also you'll understand. And maybe I am having some poll, so you can feel that nasality kind of thing also. So those kind of lots of parameters you can understand from a speech signal. So lots of, that's why speech is a very information rich signal, and so many informations are encoded in that speech signal. Then gender, then from that speech signal you can understand if that whether this is spoken by one very young a kid or a very aged person. So those information, whether there is some kind of pathological problems are there, all those health related problems. So all those things we can understand from the speech signal. Then regarding that, there are different speech technologies will be there. So whatever speech information is encoded, based on that, there are different speech technologies are there. Speech recognition, then spoken language understanding, speaker language identification, diarization, then emotion recognition. So different areas are evolved based on what information we want to extract from the speech signal. Now, what happened earlier days, for each task, we have some kind of specialized model. So for example, if we want to build ASR system, then we build specifically for the ASR system, and we collect data specifically for ASR, and then we build the ASR model. If we want to build an LID, language identification, then we need to build a separate model for language identification. So that's why what researchers been thinking is that, can we build some kind of model which learns some kind of unified representation or very general representation, which can encode most of the information present in the speech signal, and we can train that big model using unsupervised or limited supervised way, and then those kind of learned representation we can use for different tasks with very limited amount of data. So that is the goal. So how to achieve that? So that's the idea. A few benchmark related to speech signal, speech research. So any of you, if you want to go to speech related research, then these are the basic benchmark or database we can take, and we can start explore the speech. Now, I have taken this particular based plot for a speech signal. Here, if you see, this speech signal is the information, for example, this message part, if you see, is present in a hierarchical format. So this is a speech signal here. So this is a speech signal. So this is the a waveform and time domain waveform, and this is the corresponding frequency domain waveform. So this is one representation. This is another representation. Now, here, what that person spoke is that this sentence. Okay. Now, this is from this part to this part. This is one particular sentence spoken by one speaker. This is the message. Okay. Now, what word it is? So this word is C. So this is tried. So like that, for example, this is again C, and then this is the word level of segmentation. So this is another information. Then second thing is that this very that basic level of units which we call phones. So those are actually phones. Phones means like these are the basic unit of the speech signal. These are also marked here, you can see. So this is another encoded. So you can see it is a sentence level information. Then this is a word level segmentation. Then it is a phoneme level segmentation. Okay, so that means this speech is represented in a hierarchical format. Okay. Now, how we can represent the speech? So one, there are two approach will be there how we represent the speech, because if we see this signal here, so this is a very redundant signal. Okay, so there are lots of informations are there, and this is a very redundant signal, and from that signal we can do some kind of signal processing or some data driven techniques, so that we can get some kind of representation. Those representations we can use for our machine learning model development. Now, one such representation is male frequency Cepson coefficient. So this is one kind of handcrafted feature representation based on our some level of how we perceive the signal, sound, and all those kind of things is included to create this kind of features. Okay. And here, for example, this is a speech signal, and then can do some kind of speech emphasis. Then windowing we do to do the short-term processing, and then we compact that representation using DCT, and then we take deltas to get the temporal dynamics also, and we get one feature vector called MFCCs. Okay, so this is handcrafted because we are not using any data driven approach to generate this. We're using purely signal processing technique to derive this. So, and this is very predominant important feature, and it will have been using from long time for developing different kind of speech technologies. This is the short time processing, then male filter bank, then MFCC vector of a signal. So another representation, the simple spectrogram representation. So that spectrogram representation also can be fed to the machine learning model, and we can learn the technique. So these are, and there are lots of this kind of handcrafted features are there. This LFCC is there, or different this kind of techniques where signal processing techniques are there from which we can derive different speech related representations. But this MFCC is like very well known. That's why I mentioned that. Then another approach will be data driven speech representation. A very simple way, if we can say what is data driven speech representation. For example, you need to do digit recognition. Okay, so we have very simple way I'm saying. So we have digit recognition system. So from 0 to 9 we need to recognize, and then what we can do, we can collect different way of speaking of 0 and different way of speaking 1. Similarly to 9 we can speak different ways, or from different speaker we can take voice from different 0 or different 1, different 2, like that we can collect some data. Let's assume for 0 we have different recordings of 0 from different speaker. Then let's assume we are having some kind of 100 such recording for 0, 100 such recordings for 2, and then similarly for 9, 8, 9, 8, 9. Now, whatever those 100 recordings are there, we can take the MFCC factors. So that is a basic representation of speech, and we can take the MFCC factors. Then what we can do, we can compute the Gaussian mixer model of that particular or assume we can build some kind of Gaussian model. Simple one Gaussian model we can build. So if we represent that whole MFCCs, whatever from 100 recordings, to just one Gaussian model. Okay. Now, what we can do is that mean of the Gaussian we can take as a representation of the particular 0. So that is called as data-driven representation. So likewise, we can take that kind of mean vector for 1, mean vector for 2, then mean vector for 3, like that we can take for 9. This is very simplest way of saying actually. And then what we can do, for example, one unknown person speak 1, 0, then what we can do, we can take maybe then what we can do, we can compute the MFCCs, and then we can compute the similarities between all those mean vectors. So wherever we are getting the similarity, maybe that you'll say like this is the that person spoke that person spoke 0, or that person so something like that. So this is one kind of data-driven representation. And on top of, since we need more variabilities, then we can use Gaussian mixer model, mixer of Gaussians. And then if we have 10 Gaussians, then we can take concatenate the mean of whole 10 Gaussians, and then we can represent the 0. So there are different techniques are there. One technique from this GMM to techniques called total variability space, where we can have I vector. I think Azhar already discussed this kind of stuff like yesterday. And then these are called data-driven representations. Now, what is the difference now for the self-supervised learning? So self-supervised learning-based representations also data-driven speech representation. Now, what is the difference that we are going to learn? So for data-driven speech representation, there will be different approaches will be there for, as I mentioned, I vector representations, or for speaker and language, there are other representations such as X vector. So there are different methods are there. If you study some language or speaker related papers, then you'll get them. Now, before going to that, I'll just recap what foundation model is. As I mentioned earlier, what we used to do is that we build separate model for separate task. For ESR, separate, then LIB, then speech enhancement, then language identification, then emotion recognition. But that is a very costly stuff. So for example, in our company, if I want to build a model for speech recognition, then we need to collect the data from our in-house setup, or I need to buy from a different vendor. And that is very costly, and it is very time consuming and involve very rigorous process in that. To do the manual annotation of the data, because for each audio file we will be required one kind of transcription. For emotion, what we require for one audio, we need what emotion it content. Okay. So this is very difficult stuff and it's very time consuming. And we need to repeat the task for every all other different task we want to build. Now, what this foundation models leverage, it leverages all the unlabeled data available in the open source or available in private setup, and take whole amount of unlabeled data and build some kind of model which can give some kind of general representation of the speech, and we can use those more representation for different downstream tasks. And all of us, we know about this for NLP, the GPT model, then BART model. So those are called foundation models, and those models you can use for different tasks, maybe sentiment analysis, then parser switch tagging, or different tasks you can use for that model. Now, this self-supervised model, this self-supervised learning has emerged as a promising technique to build the speech foundation models. Now, what this SFL is, we'll discuss next. Now, before discussing the self-supervised learning, let's refresh our machine learning knowledge. Now, there are two, actually, the reinforcement learning is also there, but we just assume there are two categories of machine learning algorithms. For example, supervised learning and unsupervised learning. Okay. So in supervised learning, what we need is that if we have one task to classify, for example, apple versus mango, then what will be required? We need level data for apple and for level data for banana. And we need, maybe for apple, we need hundreds of examples. For banana, we will be required hundreds of examples. And then we build one model, maybe one classifier, for example, couple vector machine or decision tree or a multi-layer perceptron network or any kind of machine model we can use to train that model to classify that to class. Okay. That is called supervised learning, where we need levels. Then for unsupervised learning, for example, this k-means clustering, we don't know how many true levels are there, but we assume from the data and we do some kind of data analysis, and then we feel that there may be 10 categories, and then we use some kind of this k-means, for example, we use k equal to, for example, 10, or Gaussian. In case of Gaussian mixture model, we can use so for example 3 Gaussian, 4 Gaussian, like that. So that distribution we don't know, and we are going to model that distribution on that unlabeled data. So these are the two paradigms. In the accuracy or that performance is generally for supervised model is good, but we need more level data, which is costly and time consuming task. Unlike supervised, in unsupervised case, we don't need any level data, but performance is generally low. So how to take advantage of both, and that is the for supervised, different techniques will be there. There are different tasks for supervised learning, for example. Then now this is the traditional way of doing machine learning. So what we do, we take the raw data, for example, speech and image, and we'll have some kind of feature extractor. So in speech, we'll have that is MFCC, for example. MFCC is the one feature extractor. This is a signal processing based approach. In image, maybe it may be hog or some different kind of representations. Then we have this one factor here. Okay. Then we use some kind of predictor. So this predictor may be SVM, as I mentioned, then MLP, like that. Then we have levels and we build a model. So we need data level pairs. Then for there is another ways we have called end-to-end models, where we have raw data, and then we feed this directly, feed this raw data, that means this whole signal, speech signal, to the model, and there will be some kind of feature extractor. We can assume those are feature extractor, for example few CNN layers which will encode the representations, and then there will be some fully connected layers to project to particular class, whatever you want. These are the levels. So similar to here also, we need data pair levels, but we can learn the feature extractor jointly while training the levels, while training to predict the levels, we learn the feature extractor as well. Now these are the two approaches, but in the both approaches we need data level pairs. Now what is the difference here? In self-supervised learning, what we are doing is that okay, so here we are having this data level pairs, and then these intermediate representations we are having. Even for end-to-end also, we can take out this intermediate representation, and we can do transfer learning for other tasks. Okay, now in self-supervised learning, what is not there, that is the level. So that data comma levels, that data level pairs is not required for in case of self-supervised learning. So how we will do that? We will have some kind of visualization that we'll understand. But for this as a block diagram, we have this some kind of feature extractor model. This feature extractor model, similar to earlier models, it may be CNNs, few CNN layers. Then we'll have some kind of representation, and there will be some kind of pseudo predictors. So these pseudo predictors means we need to generate some kind of labels from the data itself. So whatever the raw speech signal we have, so from that raw speech signal itself, we need to generate some kind of labels. That means we need to specify some task which this model should optimize, and we'll get some kind of representations. Then what we'll do in that, this step is called pre-training. And then in that, when we are going to use that model for the downstream task, what we'll do, we'll take out this model, this feature extractor model, and we feed the raw image, raw speech, and then we'll get some kind of representation. And we'll use this representation with some predictor, maybe linear, some linear classifier, maybe this logistic or any linear classifier we can use, or MLP or SBM we can use as a simple predictor. And then we need some kind of small amount of data here. So here we need huge amount of data. Here we need very small amount of data to actually build a model for that particular task. Now, what is the motivation for building this kind of model? Is that currently this DL one motivation is that now we have huge amount of data, how to use those data for to learn some representation, general representation. And then another thing is that can we learn some kind of representation which can automatically discover from the data. Then this representation learn something important concepts, maybe intermediate concepts, or which will be very much useful for different downstream tasks. And another thing, maybe this supervised learning might be very biased to different tasks. So whatever model you are going to build for that particular task only, it will be biased. For other tasks, it may not be. If we do transfer learning also, it may not be that accurate while doing that. And this is the one of the main vision for that. And another thing is that if we want to build some technology for a very low resource setup, maybe for pathological speech or a language where data availability is very rare. So for those situations, this kind of technologies will be very much helpful. And specifically for speech, it is a high dimensional long variable length sequence, and we have different kind of variabilities, speaker variabilities, recording condition, XA, and then language, or different paralinguistic things. So different variabilities are there. So how to model those kind of things, and then we can create representations. And another thing, if we see here, this is a graph from I forgot to put the reference here. I'll do that in the updated slide. If we see here, then if our number of, this is the number of hours, and this is the WR decrease. So when we increase the number of hours to train AS, this is for ASR system, and this is WR, since it is a error rate, so lower is better. So if we have more amount of data, then you can see our WR is less. But if we have very small amount of data, then you can see this WR is high. Okay. So what we can feel is that, so these are the languages where database data availability is very less. For example, maybe some African languages, or here in our Assam, for example, this some northeastern so some languages where language data is availability is no data is available, actually zero resource, we can say. So for those setup, how we'll build a model. Now coming to what the self-supervised learning. So in case of supervised learning, we create levels from the from our side. But in case of self-supervised learning, what we do is that we create levels from the data, input data itself. So that so labels are the part of the data. So we are not going to manually create, and we can have some kind of automatic method to create the levels from the data itself. And generally what's done, for example, this is a speech signal. So there are different tasks will be there. So one task, for example, so this is a speech signal, and you show the model this part of the signal and ask the model from this part of the model, ask the model to predict this part of the data. So here different techniques will be there. One technique called generative, one technique called predictive, and one technique called contrastive. Okay, so there are different ways we can learn this kind of models. This generative models will be, you show this model to, you show this part of the model, this part of the data to the model, and ask the model to generate this part of the data, and then you can do some kind of checking whether this is actually it is. You can check with the some kind of L1 or some kind of loss with that correct true versus this predicted one. Then second thing, you can ask the model to predict this one. So we can have some kind of discrete representation of this particular area, and then we can ask the model to predict. And another approach is called contrastive, where you show this part of the data and you ask the model to predict this part of the data. But what you are going to do is that if for example, this is one sentence and you are taking some reason from the another part. So if it is related to that particular speaker, or for example speaker or particular same sentence, this will be your positive class. If you are taking that reason from a different part of the other audio, or for example other part of the audio, it will be a negative sample. Then you ask the model to squeeze or for example whatever the representation we are learning, if that representation are if it is positive classes, then you just ask the model to close apart, and then if it is negative samples, then you just ask the model to make long distance or something like that. I have a slide for that, I'll discuss that. Then there are different ways you can generate the task. Then there will be two tasks. One task will be pre-test task, which will be your pre-test task or auxiliary or pre-training task, where we use data itself to generate the levels, and we assign some task which and that task that model should optimize and solve it. and that task should not be very simple, so that it should not do any kind of interpolation of the data, okay, and it should learn from that data. Then in the fine tuning, we take the representations, or we call the embeddings, and then learn by that model, and then you use that model as a starting point for your downstream task. Okay. Now, from speech, from image, actually, it's easy to learn. So how this task is specified? So to learn the representation. So for example, here in case of image, so what generally it does is that you divide one image to different paths. Okay, so one image will be there. You just divide into maybe 3 by 3 grid, for example. So it will be 9 paths. So you ask the model to mask the middle paths of the image. Okay, you mask the middle paths of the image and show the model the or other whatever patches will be there surrounding to that, and ask the model to generate that model, that particular image. Okay, that paths of the model. And while doing that, it will learn those cues. For example, how this cat image will form, what will be the curvature of the particular this ear, for example, and these corners, and then what will be the structure of the face. So all those basic cues they will learn. Okay. Apart from this angle, then age, all those features also it will learn. So this is one task. So there, like that, there will be different tasks will be there. Another task will be, for example, in case of video. So we have one video sequences where, for example, 100 frames will be there. So you shuffle that frames and then ask the model to correct that. Okay, so in doing that, it will learn what its general video representation will be, or what the video is actually. Okay, so that kind of concept that model will learn. And then and for image, how it formulate is that, for example, in word to vec, which is very old kind of self-supervised learning based method, where this kind of pairs should be there. You show this model A and Brown and ask the model to predict the quick word. Then in case of autoregressive modeling, for example, these all GPT models, so it will show this part of the sentence and ask the model that impossible word. Then coming to that mask language models. So here there is no masking is happening, and but here what it is done is that it is masking a some random parts of the sentence. So for example, it mask this part or this part, and that more you can show this other part of the sentence and then ask the model to predict. So we need to our label will be this one, and our input will be this one. So this is mask, this is mask. So this is your input and this is your output, and we need to optimize that through a model. Then another task will be the next sentence prediction. So for example, I am going outside. So label should be like that. I am going outside. Then I'll be back in the evening. So this is correct actually, because this and this sentence is related. So that's why this is score is yes or 1. And I am going outside. You know nothing. Jon Snow. This will be 0. Okay. So like that we can generate. So for example, if we have one novel, then from that novel we can generate this kind of data with some automation, and we need no need this human annotation or something. So this is the formulation. And in case of speech, how it is formulated is that, for example, let's see this one. So this is on this is the output, and this is the input, and this is the output. So and we need to predict this part of the speech signal by the model. Okay. And as I mentioned, this one particular loss function, which is called contrastive loss, which teaches the model to pull together this kind of similar kind of representations, and to pull out or pull apart from that representations which are different. So in case of cat and dog, we can see this dog related patches we can just pull together here. and these negative images were cat maybe. So we just pushing apart from that representation, and while doing that, it learns the that representations. Now, in most of the SSL models, the base core models will be the Jasper models. So, for example, in case of GPT, they use the decoder part of the model. In case of BART, they use encoder part of the model. And some models are there, some sequence to sequence modeling, some models will be there. They use both encoder and decoder part. Okay, so they're why they use decoder and why they use encoder. So those are actually their design choice. So which model, which encoder, whether encoder is suitable for them or decoder is suitable for them. Now, this is one good paper. So you can read this paper to understand that history of the SSL-based models and what is the current state of the art. So if we see here, started from here, then this is one of the prominent model. Then coming to this one of the prominent model. From this model, actually, this lots of attention happened from this model, especially Web 2 Web 2. Then coming to Hubert, then WebLM, or other different models will be there. Now, as I mentioned, there will be different ways we can model. One is generative, one is contrastive, one is predictive models. This web to web is contrastive, this APC is generative, and this Hubert is predictive because we are going to predict some presentations, some feature representation, and WebLM also, it is a I think it is a predictive model. Now, as I mentioned earlier, we have two steps. One is the pre-training step where we have lots of unlabeled data and we build a model and we get the representations. And in that downstream task, what we'll do, we'll freeze this model. That means we are not going to fine tune this model, but if required, we are going to fine tune. But otherwise, we'll just take this representation and we do the we take the representation and then we take some kind of downstream model, maybe simple logistic regression, and then we do the prediction task. Okay, so there are different models. Okay, so one model called autoregressive predictive coding. So here the idea is what they are going to do. So there are there is no masking concept in that time when this they use any masking concept while building this autoregressive predictive coding. What they have done, you can see this thing. They compute the MFCC, for example, MFCC or Meglock spectra for the input signal, and they will take the context from the this to this. For example, I need to get the representations till T naught. Then I'll take all the this pass context till T naught, and then pass to this model. So there will be stack of RNN layers will be there, and then we'll get the context representation till C naught T. Okay, so this is the context representation using learned through these RNNs till T naught. Then what we'll do is that we'll project this to some linear projection, some linear layers will be there, and the dimension of the linear this after projection, the dimension of the linear layers will be the same as whatever the MFCCs will have. For example, we are taking 39 dimension MFCCs, so this dimension will be 39 dimension. And then we'll take this part of the MFCCs. For example, we are going to predict for E naught plus K, and we take out this part of the MFCCs, this vector, and then we'll do the L1 prediction error. Okay, so for whole T, it will be the summation of whole T, and then this loss we are going to minimize. And while doing that, it will learn the contextual representation, which we can use for different tasks. So this is for the autoregressive predictive coding. Then for web to web, the idea of masking came. Then what? And then another thing is that they have done very cross-linguistic, huge amount of data they use to build a model, and they use the contrastive loss to. Earlier they use L2 loss because there are two. They are generating and then they are checking the error. And here, what they are doing, they are using the contrastive loss. That means what? They are taking the whatever there's similar kind of patches, they will pull together. Otherwise, they are pushing together those negative samples. So this is the architecture, basic architecture. So you can see how much hours of labeled data, unlabeled data they have used. So it's very huge. And similar, unlike APC, now this at this Web2Vec at 2020, because transformer came, so they use transformer for this contextual representation and CNN for feature representations. We can see here this masking came, so that's why this CNN, this will be XT, and here they are using raw input. Unlike APC, they use some kind of representations, but here they are using raw audio, and they use some kind of CNN layers to make the latent representations called ZT, and this latent representation they mask. Okay, now what they will do is that they will show this and this to this context model and create something CT, and this CT we need to predict. Okay, we need to predict this masking part, but we are not going to predict this mask part directly, but we are doing some kind of quantization. Okay, so when we do quantization, it's easy for the model. It no need to predict the continuous kind of variables. So when we do the this quantization using PQ maybe, so we are having some kind of categorical representations. So that categorical representations we need to predict using this, and then we'll have some kind of loss, which is this contrastive loss. Along with contrastive loss, they have some kind of diversity loss. How to, I mean, this while building this PQ, actually they to have some kind of diversity, they use that. Okay. Now, so this representation, the CT, now after training complete, the CT you can use for a single audio, use as a representation for your task. Okay, now then this CT, that representation is called embeddings. Now that embeddings you can use for different tasks. So here this author showed for some kind of language language classification task, where you can see this kind of these languages are clubbed together. For example, this kind of languages are clubbed here. This kind of language are there. The Chinese is here. You can see this, each dot is a one language. So through learning through that Web2Vec representation, we can actually identify those languages. So that's what the idea. And even they visualize the co-occurrence between this, whatever the discrete latent representations they got. So they found is that they clearly represent those E, all those kind of sound units properly. Then very good thing is that, so this is a supervised ASR, this color, and this is a Web2Vec based model. Now we can see here, this model is built using 100 hours of supervised data, and this is built using 960 hours of supervised data. So obviously, like if it is 960 hours of data, the WR will be less, will be good. But what we saw is that if we use Web2Vec model, which was trained with very huge amount of unlabeled data, and if we use only 100 hours of data, then we get less score than the supervised model here. And also, if we use only 10 hours of data with this Web2Vec model, we are actually getting less WR compared to this 100 hours of speech data. So now assume if we have some kind of 100 hours of data or 1 hour of data, still we can get some kind of comparable result with that supervised based model. So that means what? If we have very small amount of row resource setup or row resource languages, we can at least we can build some kind of model which may not be may not be possible with the supervised way if we have same amount of data for that particular language. So that's the motivation. So here we can read this paper, we can get this benchmark results. So how much they are getting for 10 minutes, 1 hour, then 10 hours, like that they have. So another concept called self-training. So what it means is that we build one web-to-web model now, and then we can use that model to transcribe a set of unlabeled text, unlabeled audio, and then whatever, and those labels we can say as a pseudo labels because those labels may not be 100% correct. And then again, retraining this web-to-web model is the called self-training. So if we do some kind of filtering of those transcriptions and then you iterate that process over the time, so your model improvement will be good. So that's called self-training. And here we can see this kind of we participated like 3-4 years before. This is very comparable result we got with this web-to-web model. And this web-to-web model is based on Indic languages because earlier other models, whatever I discussed, web-to-web, that original model. So those are different languages are there, but this team from Xstep, they build this model. Even for AI for Bharat, they also build this Indic web-to-web model. So it is very much good. That can also be used. Now coming to Hubert. So in Hubert, I'll go directly to this, just to this concept. So in Hubert, this is a whatever the data they have gathered. First, they will extract the MFCCs and they will do some kind of k-means clustering. So once they will do the k-means clustering, they will have some kind of category to map. So this k-means maybe this all those k clusters, whatever they are getting. So those clusters they will take as a reference, and then they will ask the model to predict those. Okay. And then they will have some kind of loss function in the first epoch. In the second epoch, what they will do, it is written here, is that output of the previous training epoch is used as a output level for to train the model. So if you read this blog, actually, it's very clearly described here. So here also you can see this web-to-web, this compared to web-to-web, this Hubert model is better compared to this web-to-web model for this kind of data. You can see here with 1 hour of data, at least we are getting some 4 WR. Another model is there, Hubert. So this model is trained with this Hubert technique, but with multilingual setup. So this is very good model for the language recognition task. Then another model called WaveLM. Earlier models, whatever is done, so those are actually masked language prediction, and for one particular audio, they do some kind of masking and then try to predict and do the optimization. But here what they have added is that they added another task called speaker training to just have some kind of speaker so that this representation, whatever it is learning, so it has some kind of speaker representations also. So that's why what they are doing is that, so they are assume, for example, one audio contains one speaker, and then whatever access we are having from that particular one audio will take as a positive sample, And then the next audio, we are assuming that as a reference speaker. Obviously, there will be some kind of mixing strategy they are using and to train that model. And while doing that, and they showed is that for speaker verification, this model is better. And now what they showed is that these layers, for example, you can see that for speaker verification, these four or five layers. Hello, officer. Okay, so and what we can see is that these later layers is more related to this phone recognition, this ASR kind of task. Okay, where we need to generate the transcription. So for those, actually these latter layers will be more useful, and for this kind of speaker verification, this kind of task, these middle layers are important. That's what they showed. So this is another paper where from Simji. So this paper evaluate evaluate how for different tasks which foundation models will be effective. So for different speech foundation models are there. So what is how we can compare those models. So this paper is very useful. And in this superb benchmark, so they have shown like how different models can be used for different tasks. For example, intent classification. So this is a base report if you want to start any new work on top of that. So this is the table actually, or you can see there are these many models are there, and they have done very good comparison of that. Now, second thing is that once we learn those representations, what those representations are learning, and for each layer, for example, which layer will be effective for which task. So to study those, that is called a neural representation analysis. Okay. Now, when Matthew sir took the lecture, I think he already discussed about for different tasks. Now, there are actually two ways we can do that to check how these neural representations, capture those linguistic or acoustic properties. So for that, there are two tasks, two approach. One is called the probing task, and another approach is called the similarity approach. Okay, so now what is a probing task? So let's take Web2Vec as a model. And what we want to identify is that our task is for the emotion recognition. Okay, I want to see which layer is encoding the emotion information and what kind of emotion information it is encoding, and how much it is encoding. All those information, if I want to see, then what I'll do is that we'll have some kind of level data for emotion, and we'll take the Web2Vec model as it is. We are not going to fine tune that, and then we'll take for each audio we'll take the representation, and then we can have some kind of statistics, maybe mean we can take, or max also we can take. There are different three functionals we can take, and then let's assume we are taking the mean of that. For whole audio, we'll get different feature vector Web2Vec representations or embeddings, and then we are taking the mean. Okay, then for 3 emotions or 4 emotions, whatever we are having, and we are using a linear classifier, maybe any kind of linear classifier or SVM we can use to predict the properties of interest. So in case of here, the properties of interest is emotion. So this is called a probing task, and then we can analyze for each layer what we can do. Then for the similarity approach, in similarity approach, we don't require any kind of annotated data. So when we use this similarity approach is that, so if I have this Web2Vec model, and if I want to learn, for example, this first layer embeddings, how it is correlated with the last layer embeddings. Okay. Or if I want to see this wave-to-wave model, first layer, how it is related to Hubert, second layer or third layer of the embeddings. Okay, so this kind of inter similarity or intra-similarity, this kind of analysis, if we want to do, then this approach is called similarity-based approaches. Now, and in that case, actually, we don't need any kind of annotated corpus. And then we can do some kind of layer, as I mentioned, layer-wise analysis. In wave-to-wave, this base model, it has 12 layers. For large model, it has 24 layers. So for emotion recognition, what this I have taken from this paper, I think Interspeech 2024 or 2023, I think. What they found is that they have done the study using Hubert model, and Hubert, you can see this graph, red curve. Okay, so this is like this. So we can see this this L0, L1. These layers are the transformer layers, and this L0 is the CNN last layer of the CNN. CNN, that feature extractor is there. So this is the last layer. Now we can see here this emotion is emotion recognition. This SER accuracy is more in this sixth layer, maybe sixth or fifth layer. It is more, and then again it is decreasing, and again a bit increasing and decreasing. Okay, so it is increasing, and then it is peak at this point. So that means what, this emotion kind of information is captured more by this six or five layer. Okay, so this is very important. Now this is for emotion recognition. So there will be lots of different tasks will be there. So maybe another task, maybe for example, keyword spotting, or maybe intent classification, or for example, in paralinguistic, in case of pathological speech, for example, dysarthria. So in dysarthria, for example, or hypernasality, how these encodings are related, or how, which information, or when which layer is encoding more information. So this kind of analysis actually now very promising, and people have been doing now. So this is the one way. This is the one thing. Then another thing what people have studied is that how similar those representation with the male fractal features. Okay, so there are different models. So we can see here they are taking the similarities. Okay, it should be actually similarity based approach. I sorry for that. So this is not probing task. This is a similarity based approach. So here you can see this. Okay. This is, let's see for wave to wave. So this is wave to wave. This is wave to wave. So what they found is that, okay, these are the transformer layer, and these are your CNN layers. Okay. So now what they found is that this fifth and sixth layers actually encode this MFCC kind of thing. Okay. And it is same for all the layers actually, all the models. If we see wave to wave, Hubert wave, for all the models actually, this fifth and sixth layers of CNN is actually learning that kind of male spectral feature kind of thing. Okay, so that means what is that this anyway this CNN layers actually it is learning the representation, this latent representations. Those are actually you can say feature extracted, but this transformer layer actually learning the temporal dependencies, that contextual representations. So that's why in case of emotion, this is more related to your contextual kind of temporal dynamics kind of thing. So that's why it is more shifted to the this kind of thing. So in case of emotion recognition, accuracy is high here, this transformer layers. Okay, so it is learning them. But since this male spectra, those are features, so it is learning here in this CNN layers in that 5, 6, 4, 5 layers. Okay, so it's very interesting. Then another thing, how different representations, I mean different task it is learning. For example, these local acoustic features, maybe these local acoustic features you can assume MFCCs only, then phone identity, then word identity and word meaning. Okay, so this is related to meaning, is related to semantics. So this is modeling by here, and this local acoustic features also you can see here. This is learned by maybe in the CNN layers are learning here, or these early layers, and word identity and this kind of things it is learned by in this particular middle layers. And similar to here also, this big model. So here they are showing for the one paper, they are showing for the Hubert model for the depression detection. So in case of depression detection, they found is that it is maybe related, maybe around like 4 or 5 kind of 4 or 5 layers they are getting that depression detection properly. Now, what is my motivation, or what I want to show is that there will be different tasks. So, for example, we are doing some kind of work related to tone. So, how this, for example, for same word, how meaning is changed depending on the prosody or intonation sense or if not pattern sense. So, how actually those things are encoded, this kind of models. So, even for those also, we found this kind of middle layers actually model this kind of prosody related things, since depression, emotion, so those are also related to how prosody says or how intonation says. So maybe that's why these layers are more effective for that. And what researchers have found is that if you do fine tuning and fine tuning with some task, for example fine tuning with ASR task, and then if you do some kind of task which is not related to ASR, in some point it is improving and in some point it is not improving. In case of tone recognition, especially, it is improving. If we do some kind of fine tuning for that particular language, it is improving. But as in the last presentation, Matthew sir showed, like in some tasks, it is actually not improving if we do the fine tuning, and we are actually losing that particular information what we want to. So this is another work we did for this ICAS this year, where this we try to see because there are different models will be there. So one model will be your speech model, one will model audio kind of model, another model maybe this language model, text input, then video will be there, image will be there. So these are different modalities. Okay, so how this multimodal model will be effective for this kind of non-verbal emotion recognition. So that we try to see compared to this single model. For example, wave to vec, it is a only single modality on this speech. Okay, so we found like if we use multimodal kind of thing, then this performance improve, and we propose some kind of mechanism how to transport from one particular model to another model, and we found like we are getting good result if we do the multimodal fusion kind of thing. Now another thing is the similarity based approach. I discussed actually. So we can here you can see this second figure. Here it is a bit interesting one. What they have done is that they compute the similarity between this wavelength embeddings with a already trained speaker model. So already trained speaker model means if you are from speech background, and this as I had also discussed, I think in the last presentation, X vector models will be there, or different I vector, or this Ikapati DNN. So these kind of models are there. So those embeddings, those are specifically designed for speaker recognition. So if we check the similarity between those representation with this wavelength representation, so what they found is that so these layers are actually these similarities are like that. So these layers are not learning related to speaker. So these layers are learning, these layers are learning, these layers are learning. So they found this kind of similarities. Then Another now, OP sir, if you have any, if anyone any question, maybe you can take.
Yeah, participants, if you have any doubt, please go ahead with your query. Till now, if you have any doubt. Okay, so I think there is no doubt. Please continue.
Okay, okay, sir. Okay. Uh, so another aspect in case of this SSL-based pre-training is called analyzing the domain shift. So what do you mean by domain shift? Is that this kind of problem we face generally every day. Uh, for example, if we want to build a ASR system and your training data is from headset recording, okay, and whatever your test scenarios or where you are going to deploy the model in the actual scenario, those may be your telephone channel or in a different recording conditions. So in that situation, what happened? That it is called a domain shift. Okay, so our recording, our that model development data is headset recording, clean set, clean room environment, and while the deployment, it is a different set of environment or recording. Whole thing is different. The noise will be there, everything will be different. Okay, so these SSL models, when people studied actually, if it is there is domain mismatch, so there is very gap between this performance. Okay, so in the same domain, that performance will be better. In that other domain, the performance is not better, even if we train with huge amount of data. So then, what is the solution? Is that so? What we can do is that if I want to build a model for telephone channel, for example, then what we can do, we can take the telephone channel data, maybe unlabeled telephone channel data, because that is that is easy to get compared to this annotated one. Then what we can do, we can take this web to wake model or Hubert model, and we do some kind of extended pre-training. So extended pre-training means you take the web to wake model as it is from the repository, and maybe that web to wake model is trained till 10 epoch, and using your own telephone channel data, you train another maybe 1 or 2 epoch. So this is actually depends on your data and then amount of data, and there will be different parameters to check. But if we do that kind of thing, then what this model will learn, at least uh, it will learn something related to this telephone channel data, and this way actually your performance will be boosted by several factors. So that is one way this domain mismatch can be reduced using this kind of strategies. But another approach obviously will be like how to we can do fine tuning with the level data. But if we don't have level data, then this is one way to do that. So this is another this paper actually. This very interesting one. I think OP sir,
Yeah.
I'm done with my
So